Dear students, welcome back to the lecture series on solid state. In this session, we will continue our discussion on the powder X-ray diffraction method or the Debye-Scherrer method. So, before moving on to today's session, let's discuss the questions of the previous class. Let's begin with the first question. The Debye-Scherrer method is primarily used to study option A, liquid samples, option B, polycrystalline solids, option C, amorphous materials, and option D, single crystals. We have seen that the Debye-Scherrer method is also known as powder X-ray diffraction method or simply powder method, and in this we use a finely powdered sample, and in this finely powdered sample there will be a number of tiny crystals called crystallites. So, this method is primarily used to study polycrystalline solids. So, the correct option is option B, polycrystalline solids. The Debye-Scherrer method uses powdered sample, whereas the rotating crystal method or a single crystal method uses single crystals. Okay. So, in this method it is used to study polycrystalline solids. Now, we will move on to the second question. In the Debye-Scherrer camera, the film records diffraction lines in the form of option A, straight lines, option B, concentric circles, option C, parabolic arcs, and option D, circular arcs or Debye rings. We have seen that in this method, the X-rays getting diffracted from the powdered sample produces a cone like appearance, that is the reflected X-rays produces a cone like appearance known as the Debye-Scherrer cone on the photographic film or the detector around the sample. So, when this cylindrical film is uncoiled, you can see a series of pair of arcs situated on either side of the central X-ray spot. Okay. So, these are called circular arcs or also known as Debye rings. So, in this question, the film records diffraction lines in the form of circular arcs or Debye rings. So, the correct answer is option D, circular arcs or Debye rings. Third question. The Debye-Scherrer method is mainly used for determining option A, crystal orientation, option B, crystal structure and lattice parameters, option C, atomic number of elements, option D, optical properties. Both X-ray diffraction techniques, namely the rotating crystal method as well as the powder method or Debye-Scherrer method, is mainly used for identifying the unknown crystal structures as well as determining the lattice parameters. So, here the correct option is option B, that is used for determining crystal structure as well as the lattice parameters. Let us move on to the next question. The broadening of diffraction lines in a powder XRD pattern indicates option A, large grain size, option B, instrumental error only, option C, small crystallite size or lattice strain, and option D, high purity of the sample. So, during powder XRD, we can plot the intensity of the diffracted beam versus the Bragg angle 2 theta, and you will have the reflections from lattice planes that satisfy Bragg's law. And usually we get very narrow, sharp peaks. However, there may be diffraction lines which are broadened to some extent like this. Okay. So, this broadening is an indicative of the size of the crystallite, that is the average particle size. So, if there is a broadening of the diffraction lines, then that indicates a smaller crystallite size or lattice strain. So, among these options, the correct answer is option C, small crystallite size or lattice strain. That is, the broadening of diffraction lines in a powder XRD pattern indicates a small crystallite size or lattice strain. Move on to the fifth question. In the powder diffraction method, random orientation of crystallites ensures that option A, only one set of planes diffract, option B, many sets of lattice planes satisfy Bragg's law, option C, the intensity of diffraction is maximum, option D, no diffraction occurs. So, in this method, the crystallites are randomly oriented in every possible direction. And because of this random orientation of crystallites, there will be many sets of lattice planes that can satisfy the Bragg's law. And hence, there will be reflections from all possible lattice planes. So, the correct option is option B, many sets of lattice planes satisfy Bragg's law. In the previous class, we have seen about the powder X-ray diffraction method or the Debye-Scherrer method. We had a detailed discussion on the principle of the Debye-Scherrer method. We have seen that it is a powder X-ray diffraction technique used to determine the crystal structure and properties of polycrystalline or powdered solids or powdered materials. And this method was developed by Peter Debye and Paul Scherrer in 1916. And this method is based on Bragg's law of X-ray diffraction. We have seen that we use a finely powdered sample, and such a finely powdered sample will consist of randomly oriented small crystals called crystallites. And X-rays diffract from those planes satisfying the Bragg's condition. So, here you can see an incident X-ray beam which is allowed to pass through a slit or a collimator. The X-rays are monochromatic beam of X-rays. Usually we use a copper K alpha radiations, and these are allowed to pass through a slit or a collimator and allowed to fall on the powdered sample. And when X-rays hit this powdered sample, what happens? X-rays get diffracted from all possible lattice planes that satisfy the Bragg's law. Since there are a large number of tiny crystals called crystallites which are randomly oriented in every possible direction, there will be large number of diffraction angles as well. So, that results in a number of diffraction patterns. So, reflected X-rays form a cone like this called the Debye-Scherrer cone. And for each set of crystal planes, the diffracted X-rays form a cone of reflected rays with a semi-angle of 2 theta, as you can see in this figure, where theta is the Bragg's angle. Now, these diffracted rays are detected by a detector or a photographic film placed around the sample, and that intercepts these cones. And when we uncoil the cylindrical film, we can see a pattern of concentric arcs as you can see on the screen here. You can see that the arcs are equidistant, a pair of arcs are equidistant from this central spot that will be symmetrically situated on either side of this central spot. The intensity of the diffracted beams recorded by the detector can be plotted against 2 theta to get a series of reflection maxima as you can see on the screen. You have the intensity of the diffracted beams on the y axis and the angle 2 theta in degrees on the x axis. So, these diffraction patterns or peaks corresponding to reflections from various planes such as 100, 110, 200, etc. The diffraction pattern obtained is a characteristic of the crystalline substance under investigation, and hence this provides valuable information regarding the lattice type as well as the lattice parameters. Now, let us see the analysis of the powder diffraction patterns. We have seen that the powder method or the Debye-Scherrer method gives a series of diffraction patterns which gives information about the lattice type as well as unit cell dimensions. So, let us have a discussion on the diffraction patterns for the cubic lattices. For a cubic lattice with edge A, the distance between the planes in the HKL set, H, K and L are the Miller indices representing each plane. So, the distance between the planes in the HKL set is given by DHKL equals A by root of H square plus K square plus L square. If we take the square of this, we can write D HKL square equals A square by H square plus K square plus L square. Let this be equation 1. For a nth order reflection of X-rays of wavelength lambda at a Bragg angle theta from the HKL set, the Bragg's equation is given by n lambda equals 2d sin theta. Let this be equation 2. We have the Bragg's equation n lambda equals 2d sin theta. Now, if we take the square of this, we can write n square lambda square equal to 4 d HKL square sin square theta. So, let this be equation 3. Okay. So, first we have written the equation for the distance between the planes or d spacing given by in the square d square is equal to a square by h square plus k square plus l square. Let that be equation 1. And we know that the Bragg's law is n lambda is equal to 2d sin theta. If we square that, we get n square lambda square is equal to 4 d HKL square sin square theta. Let that be equation 3. So, if we substitute the value of d square from equation 1, we have d square is equal to a square by h square plus k square plus l square. So, if we substitute that value in equation 3, we get, so from equations 1 and 3, we will have n square lambda square is equal to 4. Instead of d square, we can write a square by h square plus k square plus l square into sin square theta. Let this be equation 4. So, from this we can write an equation for sin square theta. So, sin square theta is equal to n square lambda square by 4a square into h square plus k square plus l square. This be equation 5. So, from equations 1 and 3, we got n square lambda square is equal to 4 a square by h square plus k square plus l square into sin square theta, and from this equation we have written an expression for sin square theta, that is equal to n square lambda square by 4 a square into h square plus k square plus l square. Now, when we consider a first order reflection, so for first order reflection n is equal to 1. So, for n is equal to 1 for first order reflection, we can write sin square theta is equal to lambda square by 4 a square into h square plus k square plus l square. Okay, sin square theta is equal to lambda square by 4 a square into h square plus k square plus l square. So, if we put this lambda square by 4 a square is equal to k, that is k equals lambda square by 4 a square, then this equation becomes sin square theta is equal to capital K into h square plus k square plus l square. This be equation 7. So, we have arrived at an expression for sin square theta. So, sin square theta is equal to k into h square plus k square plus l square, where k is equal to lambda square by 4 a square. So, we have sin square theta is equal to k into h square plus k square plus l square, and k is a constant for a particular wavelength lambda and the unit cell edge A. So, this gives a relation between the Bragg angle theta as well as the values of the Miller indices h, k and l. Now, it is not necessary that the reflections from all sets of possible lattice planes are observed in the X-ray diffraction patterns of all types of lattices. While discussing the powder method, we have seen that there are a large number of reflections possible from lattice planes because a large number of planes satisfy Bragg's law. However, it is not necessary that the reflections from all set of possible lattice planes are observed in the powder diffraction pattern. And this is because if one set of planes is uniformly spaced between the planes of another set, okay, so one set of planes is uniformly spaced between the planes of another set, destructive interference between the rays reflected from the two sets can occur. Destructive interference means the reflections from the two planes will be out of phase or they cancel out each other. And when such destructive interference occur, what happens? The diffraction lines will be absent. There won't be any reflection maximum occurring, so that causes the diffraction line to be absent. Okay. So, when we analyze a powder diffraction pattern, it is not necessary that there will be reflections from all possible lattice planes corresponding to all types of lattices. And this is because if one set of planes is uniformly spaced between the planes of another set, the reflections from such planes will be out of phase or they cancel out each other, resulting in a destructive interference. And when such destructive interference occurs, then that causes the diffraction line to be absent. So, such missing reflections or absent reflections are known as systematic absences. And identification of the systematic absences is very important in confirming the lattice type. Okay. So, systematic absences in a particular powder diffraction pattern provides valuable information regarding the lattice type. Let us see a few examples. For the simple cubic system, reflections corresponding to all possible H, K and L indices are observed. Okay. So, for any value of H, K and L, we can see reflections from all these planes in the case of a simple cubic system. Now, what about a body centered system for a BCC lattice? In a BCC lattice, we can see that destructive interference from the reflections from the 200 and 222 planes respectively causes the reflections from the 100 and 111 planes to be absent in the powder pattern. So, that is the reflections from 200 and 222 planes and the reflections from 100 and 111 planes. Okay. So, they may cause destructive interference, and as a result, when we analyze the powder diffraction pattern of a BCC lattice, we cannot see lines corresponding to reflections from 100 and 111 planes due to the destructive interference from the planes 200 and 222 planes respectively. Similarly, when we consider a face centered cubic lattice, for an FCC lattice, the 200 and 220 planes respectively cause the reflections from the 100 and 110 planes to be absent. Okay. So, for a simple cubic system, there will be reflections corresponding to all possible H, K and L values. In a BCC lattice, we cannot see reflections corresponding to 100 and 111 planes. The lines will be absent from the 100 and 111 planes due to destructive interference from the planes 200 and 222 respectively. Similarly, in a face centered cubic lattice or FCC lattice also, we cannot see reflections corresponding to 100 and 110 planes due to the destructive interference from the 200 and 220 planes. Okay. So, this table shows the conditions for a lattice to show the reflection lines in the powder diffraction pattern depending on the value of H, K and L. So, let us see this. First, we have a simple cubic lattice. We have already seen that for a simple cubic lattice, there will be reflections corresponding to all lattice planes. So, the condition is all H, K and L values are allowed. That is, for any value of H, K and L, we can see the diffraction lines corresponding to all H, K and L values for a simple cubic system. That is, for any plane, that is 100 or 110 or 111, 200 etc. So, for any HKL value, we can see reflections corresponding to such planes in the case of a simple cubic system. Now, let us consider the other system, body centered cubic or BCC. We have already seen that some reflections are absent in a BCC. So, the condition is only those HKL values for which H plus K plus L is even. Okay. Only reflections from such planes will be observed in the powder diffraction pattern to a system corresponding to BCC lattice. Okay. Only those HKL values for which H plus K plus L, the sum of the indices H plus K plus L is even. For example, you can see reflections from a 110 plane 2, 0, 0, 2, 1, 1, etc. So, if you take the sum for a 1, 1, 0, h plus k plus L, 1 plus 1, it is the sum is 2. 2, 0, 0, again the sum is 2, which is even. 2, 1, 1, 2 plus 1 plus 1, it is 4. So, again it is even. So, for all HKL values in which H plus K plus L is even, you can see reflections corresponding to those planes in a BCC lattice. And the last one is a face-centered cubic lattice for an FCC lattice. Only those HKL values which are all even or all odd, that is H, K and L values, either all of it are even or all of it are odd. For example, you can see reflections from the 1, 1, 1 plane, 2, 0, 0, 2, 2, 0, etc. If it is a 1, 1, 1 plane, the value of H, K and L all are odd. And if you consider 2, 0, 0, all H, K and L are even. 2, 2, 0, again all the H, K and L are even. Okay. So, this is the condition for a FCC lattice. In a face-centered lattice, only those HKL values which are all even or all odd. Okay. So, we have a simple cubic system in which all HKL values are allowed, and in a body-centered or BCC lattice, only those HKL values for which H plus K plus L is even, and in a face-centered cubic, only those HKL values which are all even or all odd. Now, on the screen, you can see a schematic representation of the expected lines in the powder patterns of different cubic lattices. So, the first one is a simple cubic, and based on the HKL values, you can see that reflections from almost all planes are appearing in the diffraction pattern in the form of these lines. You have reflections from 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 2, 0, 0, etc. Now, consider a body-centered cubic. We have seen that in a BCC, there will be reflections only from those HKL values in which H plus K plus L is even. So, when we look at this pattern, you can see that there is reflection from the 1, 1, 0, then 2, 0, 0, 2, 1, 1, 2, 2, 0, etc. Okay. So, these are the lines, and you can see that the H plus K plus L values even, whereas the reflections from 1, 0, 0, 1, 1, 1, 2, 1, 0 are absent, and such absent reflections are known as systematic absences. Systematic absences. So, systematic absences or missing reflections are common in a BCC lattice. Now, consider a face-centered cubic lattice. In a face-centered cubic lattice, we have seen that reflections will occur only from those planes in which all the HKL are all odd or all even. So, here we have reflections from the 1, 1, 1 plane, then we have 2, 0, 0 plane, 2, 2, 0 plane, 3, 1, 1 plane, etc. So, when we look at the HKL values, we can see that either all H, K and L are even or they are all odd. So, you have 1, 1, 1 all odd, 2, 0, 0 all even, again 3, 1, 1 all odd. Okay. So, we have 3 different types of powder patterns for 3 different cubic systems. So, in face-centered also, we can see that reflections are missing for certain planes like 1, 0, 0, 1, 1, 0, 2, 1, 0, etc. Corresponding to systematic absences. Now, you can see that at K values around 7K. So, if you take 7K, there are no reflections from any plane, and also at 15K also there are no reflections in either of these lattices. So, these are not systematic absences, but we can say that there is no such plane corresponding to h plus k plus l equal to, or h square plus k square plus l square is equal to 7 or 15. Okay. So, that cannot be considered as systematic absences. It is just that the sum of h square plus k square plus l square is nothing be equal to 7 or 15. Okay. So, this is how we analyze the powder patterns. We can check for the lines present, or we can check for the systematic absences. That gives a clear idea of the lattice type. And from the, if we identify the lattice type, so from that we can calculate the lattice parameters, the unit cell edge, etc. So, this table shows the powder diffraction patterns of NaCl, KCl and caesium chloride, CSCl. Okay. So, the first three shows a simple cubic, body centered and face centered cubic lattices. So, for a simple cubic, body centered and face centered, the expected diffraction maxima are given, and below that we have the observed diffraction pattern for NaCl, KCl and CSCl. Okay. So, let us compare NaCl, KCl and CSCl with these three types of lattices. First, consider the powder diffraction pattern of NaCl. We have already discussed about the crystal structure of NaCl in the previous classes, and we know that NaCl belong to a face centered cubic lattice, and it consists of two interpenetrating FCC lattices, one of Na plus and the other of chloride ions, as shown in the figure. Now, let us compare the powder diffraction pattern of NaCl and the FCC lattice. So, for a face centered cubic, we have reflections for 111, 200, 220, 311, etc. So, similarly, if you consider NaCl, you can see similar reflections here 111, 200, 220, 311, etc. So, you can see that the powder diffraction pattern is very much similar to corresponding to the FCC lattice. So, we can say that NaCl consists of FCC lattice. Actually, it consists of two interpenetrating face centered lattices, one consisting of Na plus ions and the other of Cl minus ions. We can see that each Na plus will be octahedrally surrounded by 6 chloride ions, and each chloride ion will be surrounded by 6 Na plus ions. And since it corresponds to a face centered lattice, we can say that there will be 4 formula units of NaCl, that is per unit cell, and it corresponds to FCC lattice. Now, let us consider the powder diffraction pattern of KCl. Actually, KCl also have a similar structure to NaCl, and both corresponds to FCC lattice. However, when we look at the powder diffraction pattern of KCl, the face centered we have reflections on 111, 200, 220, etc. NaCl we have already seen that it have similar reflections to FCC. Now, just look at KCl. So, the KCl, the first reflection usually seen in a FCC lattice is the 111 reflection. But when we look at the diffraction pattern of KCl, you can see that it is absent here. The cross mark represents the absence of reflection, the tick mark represents the presence of reflections. So, when we look at KCl, you can see that the first reflection generally expected from a FCC lattice, that is the 1, 1, 1 reflection is absent in the KCl here. Okay. Whereas 2, 0, 0 is present, 2, 2, 0 is also present. So, why this difference? So, that is due to the different scattering factors of their ions. In KCl, we know that the K plus ion and the chloride ions are isoelectronic, and isoelectronic means they are having the same number of electrons. K plus have 18 electrons, chloride ions also have 18 electrons. So, they have same number of electrons. So, that means their scattering strengths are equal. The strength of scattering of X-rays depend upon the number of electrons in an atom. So, if two atoms have same number of electrons, that means their scattering strengths are also equal. So, when the scattering strengths are equal, they cancel each other when their reflections are out of phase. Okay. So, here what happens is the reflections from the 1, 1, 1 planes of K plus and the reflections from the 1, 1, 1 planes of Cl minus cancel out each other because they have same scattering strength. And since they cancel out each other, you cannot see a diffraction line corresponding to 1, 1, 1 plane in KCl. Okay. So, though KCl belong to FCC lattice, the first reflection we expect from a FCC lattice is generally the 1, 1, 1 reflection. But here in KCl, the K plus and Cl minus ions are isoelectronic, that is, they are having the same number of electrons. And when the species are isoelectronic, they have equal scattering strength, and when they have equal scattering strength, the reflections from such planes will cancel out each other. So, when we consider the K plus and Cl minus ions, the 1, 1, 1 reflections from the K plus and 1, 1, 1 reflections from the Cl minus will cancel out each other, causing the diffraction line to be absent in the diffraction pattern. Okay. So, due to the cancellation of scattering for certain reflections, the KCl powder diffraction pattern looks similar to that of a simple cubic lattice, although it corresponds to FCC lattice. But there is no such problem with NaCl, because in NaCl the Na plus and Cl minus are not isoelectronic. Na plus have only 10 electrons, whereas Cl minus have 18 electrons. They have different scattering strengths. So, the reflections from the 1, 1, 1 planes of Na plus and Cl minus will not cancel out each other, and hence you can see a reflection corresponding to the 1, 1, 1 plane in the diffraction pattern. So, though NaCl and KCl both belong to FCC lattice, the diffraction patterns differ in NaCl as well as KCl. Now, let us see the diffraction pattern of cesium chloride. So, in cesium chloride, you can see that there are a large number of reflections corresponding to almost all planes. You can see 100, 110, 111, 200, etc. So, you can see that by merely looking at the table, the powder diffraction pattern for CSCl indicates a simple cubic unit cell, and it is actually so. So, on the screen you can see the crystal structure of cesium chloride, CSCl. So, the structure can be visualized as two simple cubic lattices of different ions, that is Cs plus ions, one simple cubic lattice consisting of Cs plus ions and another simple cubic lattice consisting of Cl minus ions that interpenetrate each other. And in the structure we can see that each Cs plus ions is surrounded by 8 chloride ions at the corners of its cube. it may feel like that the Cs plus ion, the cesium is at the center, at the body center, surrounded by 8 chloride ions at the corners. Similarly, each chloride ion is also surrounded by 8 cesium ions at the corners of its cube, and it may give rise to a BCC structure, or we may call that it is a pseudo BCC structure. Actually, in each lattice the atoms are present only at the corners, but because of the interpenetration of the two simple cubic lattices, we may feel that the cesium ion is present at the body center surrounded by chloride ions at the corners. Similarly, the chloride ion is present at the body center surrounded by cesium ions at the corners. So, we may call that it is a pseudo BCC structure, but actually it is a simple cubic structure. And each unit cell effectively contains one cesium ion and one chloride ion. So, one formula unit of CsCl. Okay. So, in this class we have discussed and analyzed the powder diffraction patterns of 3 cubic lattices as well as NaCl, KCl and cesium chloride. Now, let us have a discussion on a few questions based on today's topic. First question, the number of formula units per unit cell in the NaCl structure is option A 1, option B 2, option C 4 and option D 8. Which of the following statements is true regarding the systematic absences in the diffraction pattern of NaCl? We have 4 options. All odd and even H plus K plus L reflections appear. Only reflections with HKL, all even or all odd appear. Only reflections with H plus K plus L odd appear, and only H00 type reflections appear. Third question, in the cesium chloride structure, the first reflection in the powder diffraction pattern corresponds to 100, 110, 111 and 200. Fourth question, a powder diffraction pattern showing peaks corresponding to 100, 110 and 111 planes is most likely to belong to 4 options: face centered cubic lattice, body centered cubic lattice, simple cubic lattice and hexagonal close packed lattice. The last question, if the first few observed peaks in an unknown salt match the FCC reflection conditions, the structure is likely to be similar to NaCl, CsCl, zinc sulfide ZnS and NaF. So, try to find out the answers for these questions. We will discuss it in the next class. Thank you.